In the last video for this week, I would like to present some basic properties of this Kullback-Leibler divergence, a quantity we discovered in the previous previous two videos actually. And it's a very important quantity, one of the most important ones in information theory. Later we'll see many of other information quantities will be related to Kullback-Leibler divergence, including our favorite entropy. So in this short video, I will only present the properties without proof, and later we will go later when we study properties of information quantities, we will give you. I will give you all these proofs. Okay. So first property of Kullback-Leibler divergence is the data processing is called the data processing inequality. In fact, any quantity which promises to measure distance between distributions must satisfy data processing inequality. This is a reasonable expectation. Okay, so what is the data processing inequality? It's very simple. It says distances between distribution decreases when you further process their samples. So when you further process samples by applying any randomized mapping to the samples, by passing them to the same channel, the distributions, the underlying distributions will come closer. So any downline processing will actually make the hypothesis testing problem harder because distances will shrink. So what does it mean? It sounds a little bit counterintuitive because signal processing engineers would always process the signal before they apply some test to it. So is that processing only making the problem harder? In fact, not. The purpose of signal processing is something else. The purpose of signal processing is to look for these transformations which minimally reduce the distances while making the problem of hypothesis testing computationally easier. This is a heuristic reason I'm giving for signal processing. It's a broader field. But this heuristic is somewhat surprising to begin with, so you should take some time to digest it. Any processing on signals which is independent of the underlying distribution will make the distributions closer. So this agrees with our heuristic that these distances determine how difficult it is to test between two distributions, since we apply test to process samples. Okay. So let me formalize this data processing inequality. Let P and Q be two distributions on Y. So this P and Q are two distributions on the same alphabet Y. And consider this channel W. This represents our downlink, which represents our processing. So what W does is looks at Y and produces something from this alphabet Z. It's a fixed channel representing a data processing operation. So this data processing, for instance, can be that I add some random noise to the sample. So if it's a continuous observation, I add just some Gaussian noise to it. So then we can show that both total variation distance and Kullback-Leibler divergence satisfy these inequalities. These are called the data processing inequalities, sometimes DPI for short. The distance between W of P, the output distribution, when P is passed through W, and the distance between W of Q, which is the output distribution when Q is passed through the channel. So this W of P, remember, is a distribution on Z. This is given by summation over Y, W of Z given Y, Py. Okay, that's our definition of W0, W of P. So W of P and W of Q are closer than dpq. We can show this by just triangular inequality. And similarly, under Kullback-Leibler divergence as well, W of P and W of Q are closer than dpq. So any channel which will add noise, so channel can be thought of as a noise. This channel doesn't depend on P and Q. So it doesn't help you distinguish these P and Q right away, and it will make these things closer. Operationally also, you can verify these inequalities. We have already shown operational meaning of dpq in terms of the expression for P star. So any Bayesian test, so it's the minimum probability of error over all Bayesian tests is related to dpq. Now consider those tests where you first pass P through W and Q through W, and then use the optimal test for W of P versus W of Q. The probability of error for this class of tests can only be larger than the probability of error if you work with P and Q directly, because this allows more tests. It doesn't force you to pass through this W. And therefore this D can only be smaller than this. But these are very easy to remember, these inequalities. We'll give justification for them again. It just says that distances shrink when you process the data. These are called data processing inequalities, and processing the data here refers to passing through the same channel W. Okay, this is the first property. The second property, which is very useful, is the one which relates Kullback-Leibler divergence to total variation distance. Earlier in an example for binary case, we saw that dpq is at least 2 by ln2 total variation distance square. In fact, this bound holds for every distribution. So this is called Pinskers inequality. It relates total variation distance to Kullback-Leibler divergence. And if you ignore the constants of 2 by ln2, which I make mistakes with all the time, if you ignore this constant, what this says is that dpq is more than total variation distance square. Okay, so dpq, you can think of it roughly as total variation distance square. So dpq behaves roughly the same as square of distance. Okay, so it's roughly like a square of distance. So what is special about square of distances in Euclidean space? So here is the Euclidean distance, summation over I 1 to n xi minus yi square. This is a Euclidean distance between two n-dimensional points. Maybe I should call it d so that we think of d-dimensional points. This is a distance square. The Euclidean distance is the square root of this. What is special about the square of distance? Do we know what is special about this? So you can think about it. There are many things which are special about it, but this is additive across dimensions. So if you have multiple dimensions, this is additive. And in fact, Kullback-Leibler divergence has a similar behavior. It is additive for product distributions. So earlier we saw that total variation distance is sub-additive, but Kullback-Leibler divergence is additive. So this is a very, very important property. It's the additivity of Kullback-Leibler divergence for product distribution. So P1, these are product distribution, P1 times P2 times Pn. All coordinates are independent, and ith coordinate has distribution Pi. All coordinates are independent, it's the second part, and ith coordinate has distribution Qi. What's the Kullback-Leibler divergence between these two product distribution? Well, it's the sum of coordinate-wise Kullback-Leibler divergences. So this is the additivity of Kullback-Leibler divergence. So three properties we have seen: Kullback-Leibler divergence as well as total variation distance satisfy data processing inequality. There's Pinskers inequality, which relates Kullback-Leibler divergence to total variation distance square. And then Kullback-Leibler divergence is additive, unlike total variation distance, which was sub-additive. So if you combine these two properties, there's something interesting which comes out. Earlier we said that Pn, Qn, the total variation distance between Pn and Qn grows like n. That's what we were able to show. But we remarked that that bound is weak. In fact, if you combine Pinskers inequality with the additivity of Kullback-Leibler divergence, you can show that total variation distance of Pn and Qn grows roughly like square root n. Okay, you can try to show it. I'll show it later in the course. And basically that bound that we had earlier for coin toss problem, how many coin tosses are needed to distinguish a coin with bias half plus epsilon from half minus epsilon, that bound can be improved to roughly 1 by epsilon square by combining this Pinskers inequality and additivity of total variation distance, additivity of Kullback-Leibler divergence. Okay, this is the last thing I wanted to present this week. In the next week, we'll continue with our discussion on connection between statistics and information theory. In this week, we basically define different versions of hypothesis testing problem. We mostly focus on hypothesis testing, although we define the estimation problem as well. And for the first version, which was Bayesian, we discovered that the probability of error relates to this quantity called total variation distance. For the second one, the Neyman-Pearson formulation, we saw that the probability of error is related to this quantity called Kullback-Leibler divergence, capital DPQ. And one principle that we projected was that the hardness of a hypothesis testing problem, a binary hypothesis testing problem, is related to the distance between the two distributions under two hypotheses. And this distance can be Kullback-Leibler divergence for one formulation or total variation distance for another formulation. In fact, the two are related by Pinskers inequality. Okay, so that's all I wanted to say this week. I'll see you in the next week.